So hi, thanks for coming today. I'm going to talk about designing reactive systems with Akka. Despite the buzzword compliance of the title, this is actually a talk based on practical experiences. I've been working with Akka for about 5 or 6 years now, since shortly after it first got released. I've been working with Scala for a few years longer than that. Akka is largely written in Scala, so that's why that's relevant. And probably about 17 years as a Java developer before that. I'm currently an engineering manager out at Nike, working with the group that collects all the data from these things and from the running app and all the other various activity-related apps. So if you're doing activities with Nike, the data that provides is actually going to my systems. I have past experience working at Cisco, a local company called Janrain that some people have heard of. They've been around for a while now. Another local startup called Simple, and way back in time, IBM and Tivoli. I also founded and organize a couple of different users groups, including the local Scala users group, and then a regional Scala conference that takes place here in Portland. So if you're curious about any of that stuff, come talk to me later. I'd be happy to talk about it more. But all that's just kind of setting the stage for the background that I'm coming from. I've been developing large-scale systems, very elastic style systems. A lot of the buzzwords that you hear now, microservices, whatever you want to throw at it, those things are just labels that are being applied to things that a lot of us have been doing for a long time, and I in particular have put a lot of focus on. So I want to start out just kind of setting the stage, talking about the world in which the systems that we build operate. If you've spent much time working in the enterprise world, it takes a little while to sort of step outside that and realize that the world's changed a lot. It's impossible to get away from the reality that everything is distributed right now. If you're a mobile application developer, you're a distributed systems developer, whether you like it or not. You're talking to systems that don't have the same idea of what the time right now is as what your system is. You're going to encounter problems that come up because of that. You have to understand distributed systems to be a developer in the current world. Everything's mobile. More people now are accessing your sites and services via mobile applications than just about any other thing out there. I mean, the days of desktop applications are really kind of starting to dwindle quickly. And everything's turning into mobile apps, and you're starting to see cases where what used to be web apps that were shoehorned into mobile, the mobile world, are now mobile apps that are being pulled back into the desktop world. So getting sort of what that implies for the ecosystem is important. And because of the fact that everything is mobile, everything is distributed, the world that we operate in is unreliable. I mean, things fail all the time. People are out there trying to reload, to see what the latest news is or whatever on their phone, and the reason they keep having to swipe to get it to reload is because they're probably getting failures trying to connect to the server. They don't know that's what's going on, but that's the reality that they're having to deal with. And then, of course, everything's being labeled the cloud right now. I mean, I threw that in there almost as a joke because it's just like, what the hell is the cloud anymore? It's everything that we deal with at this point, really. And then just to kind of illustrate this a little bit, this is focused on multi-threaded programming. This was a picture that was floating around Twitter maybe a month or two ago. I don't know who originally put this together. Really, this is about more than multi-threaded programming. This is distributed systems. This is the world that we deal with. This is also the world that we deal with. The networks are not clean. They're not simple. They're not straightforward. They're very complex, very messy. And chances are at some point, somebody's going to be trying to figure out where one of those cables goes, and they're going to pull the wrong one, and something's going to go offline. And stuff blows up, catches fire. Somebody will drive a backhoe through through your data line. You have to face that reality and accept it. So I'm going to talk a little bit, real briefly, about reactive software and what that means to give a little bit more context here. I mean, the idea of reactive software and reactive systems is not really a new one. It's really just a set of labels that are used to sort of facilitate communication about things that a lot of us have been doing anyways, but to put them in a context of what we just talked about. So the first thing, if you go read the Reactive Manifesto, and yeah, I know a lot of people get up in arms when they see something with the label manifesto on it, because they think, why the hell do we need a manifesto? And it's a good question. Maybe it's not necessary, but it helps to set some context and try to get people to wake up and realize that there's a perspective that they need to be aware of. This may not apply to you, but it may help when you're talking, say, to the junior developers that are coming in, or the the biz dev types who are trying to ask you why you can't just provide the features that they're asking for. So the manifesto talks about 4 key properties of reactive systems. The first one is message-driven, and this is actually probably one of the more controversial ones, but I think it's important because whether you're talking about RPC calls between different systems, so even if you're calling the database, you can model all of that as a message, and it's a good way to look at things, and it helps if you start to think in terms of messages between systems, between components, as you start to look at your system architecture and understand how things are interacting. Once you start digging into distributed systems, the message-based interaction model actually simplifies a lot of what you're talking about there. Makes it a lot easier to understand the interactions between the components of the system. Resilience is another term it can be kind of vague, but this is really talking about fault tolerance, fault handling, dealing with those server room meltdowns that happen, being able to, or I should back up and say, more importantly, being able to deal with that in a way that does not cause your users or your consumers to notice that there's a problem. That's what resiliency is about. So being able to have these transient failures in network communication and not have things fall over in a way that impacts your users. That's what that means. Elasticity, it's something that I almost take for granted now, which is funny because a couple years ago it was a pain in the neck to actually get truly elastic systems out there. But a lot of the services that Amazon and Docker and all these container-based systems are focused on is really basically about this idea of elasticity and being able to grow your system and even shrink it, for that matter, as needed to adjust to the changing load over time. I mean, users are unpredictable. You will have a sudden spike in usage that you didn't expect because maybe somebody tweeted about your app and said, "Hey, this is the greatest thing ever," and that person just happened to be, I don't know, who's the latest greatest pop star that everybody sees their tweets, and yeah, it doesn't matter, but being able to be elastic, being able to adjust to changing load over time, that's a key thing that you have to focus on, and you have to focus on it from the core. And then finally, all of that really kind of ties into this idea of being responsive. And responsiveness, again, this goes more to the user-focused piece of this than any of the rest of these. This is about making sure that your users don't have to care about any of the rest of this stuff, don't have to care about that world that I was showing the images of a few minutes ago. Being able to have your users use your system and get an immediate response, or at least what seems like an immediate response when they're trying to interact with it. You don't want them to know that, hey, my auto-scaling group just tanked, and another auto-scaling group in another availability zone at Amazon had to come up and bring up 15 more instances to handle that load. That should never be something that the user has to be aware of. Being able to do all these things lets you be responsive to the user. All right, so I come back to this idea a lot as I'm talking about these things. This is really about applying a lot of old patterns or patterns that have been out there for a long time to our new challenges. I mean, they're not necessarily all that new, but the entirety of the picture that I was describing a few minutes ago, that's new for a lot of people. That's things that a lot of people haven't had to deal with in the past. You could go deploy your servers in the data center and just assume that, hey, everything was just going to work, and you had Oracle behind it, and Oracle never fails, right? Yeah, I'm sure Patrick could talk a lot about that. So this is all setting the context for Akka, which is really what I wanted to talk about. And Akka is my chosen toolkit for building, whether you want to call them reactive systems or scalable, fault-tolerant systems, whatever. I think it's a really great choice, and I'm going to tell you a little bit about why, and then show you a little bit about how some common patterns and common approaches for building systems on top of Akka, which is not necessarily obvious if you just go read the docs. Excuse me for a second. So Akka is the simplest way I would summarize what Akka is, because a lot of people see it and they see the docs, they see the site, and they think, okay, something about actors, something about Scala, and what is all this stuff? It's hard to quite get a grasp on what Akka is. Fundamentally, it's a scalable concurrency toolkit. There's a lot more in there, but if you walk away with just one key idea from this about Akka, that's what you need to understand. So the idea here is that, one, it's not a framework. There's a lot of pieces to Akka. You can pick which pieces make sense to use and discard the rest. It doesn't matter. There's a core, the piece that brings in the actor model, which we'll be talking about in a few minutes. And that piece is really awesome, and you can do a lot with that. But there's also a whole bunch of other components that you can choose to bring in as you want to, and they're all built on top of that core. But it's not a single library either, so I don't talk about it as a library or a framework. It's a toolkit. As I alluded to, it's an implementation of the actor model, which we will be talking about in a second. This is kind of the part that a lot of people encounter, and if you've seen Erlang in the past, does anybody have experience with actors, whether through Erlang or Akka or whatever? Okay, so a few people have heard the terminology at least. Chances are you've probably actually encountered something that's actor-based at some point. It may have just not seemed obvious that it was. And then the other big thing that I think is sort of core to Akka is that it provides fault tolerance, and this is built into the very core of the system. Again, we'll be talking about this more shortly. And then the last thing that you should really kind of get is that it's distributed by default. Now, this doesn't mean that out of the box you go deploy an Akka-based system and you automatically have everything distributed. This means that you can distribute it without a lot of extra work. So if you need to take a system that you built and it's a little basic model that you built, say it's a simulation, you're trying to simulate a network interaction. Simulations are actually great. That's kind of how I got started with Akka, actually, was building simulations. But you suddenly find that your simulation takes up more memory than what you can fit on a single system. I don't want to imply that it's completely trivial, but it's very simple to then take that and add a couple more nodes and just say, hey, node A, B, and C know about each other and talk. And it's almost entirely just configuration based at that point. So it's very easy to build distributed systems with it, and the model that it builds in at the core doesn't cause any extra overhead, any conceptual overhead as you're doing that, which is very, very important if you've ever tried to build distributed systems. So I want to talk a little bit about the actor model real quick, just to make sure that we're all kind of on the same page with that. This is one of the things that, if you haven't seen the actor model before, it seems kind of foreign, and it's a little weird, and it seems almost overly simplistic. It is overly simplistic in a way, but it's really powerful, as a lot of simple models are. It's fundamentally about message passing, which is part of the reason why you start to see actor-based systems talked about in the context of reactive systems. It encapsulates, or it's about encapsulation of state and behavior. And what I mean by this is that the fundamental unit or entity within the actor model is a thing called an actor. I mean, it seems kind of obvious, but you can kind of think of it as like an object. They're not exactly the same. It's often modeled as an object, in a language that supports object-oriented programming. But that object has its own internal state and behavior, and the idea is that that's completely encapsulated, and you don't expose that directly to the outside world. So you already, that picture earlier with the puppies, and the big mess that you get into with multi-threaded programming, it's already giving you some guards against that. The key thing to take away here is that you're really trying to protect mutable state, because mutable state is where you run into trouble when you're dealing with multi-threaded programming. To a larger degree, this is really what kills a lot of people, even with distributed systems. I could probably do a whole talk just on that idea. I think there's a few out there, actually. But sort of trying to expose things as a mutable idea into the network is where a lot of distributed systems fall down really quickly. I'd say that most of them fall down from the start when they try to do that, but often isn't obvious until much later, unfortunately. And then the last thing that's important to understand about actors is that within a single actor, everything is sequential. So that actor is doing things sequentially. It's essentially got its own little life cycle, its own little loop, essentially, that it's processing the messages that are coming in. And then everything between actors is at least implicitly asynchronous. You can force them to be synchronous, but you have to actually do that intentionally. So by default, everything is async between actors. So I wanted to just kind of give you a little bit of context real quick so that we're somewhat on the same page. This is an example. It's very, very simplified, but it'll help, I hope, to kind of set some understanding of what we're talking about. I'll walk through this real quick. So a case class is essentially an immutable object in Scala. This is all Scala code if you're not familiar with Scala. It's fairly simple, but if there's anything that you don't understand here, just ask and I'll try to explain it. But so a case class here, whoops, sorry, jumping ahead of myself, hit the wrong button there. This case class is just defining this very simple message that's going to be passed around. I mean, like I said, super simple example. Don't judge me by that. So that's the protocol that I'm going to be using here with this actor that I'm dealing with here, and we'll talk more about protocols in just a little bit. But the protocol is basically the set of messages that define the interaction between the actors. The next thing to focus on is the behavior. The behavior in Akka is defined. Geez, I'm not used to this remote. Is defined using a receive block. Receive basically is just a way of defining what to do when you receive different messages. So in this case, when it gets the message greeting, it's going to print out a log message that says hello, whatever the name was that's in the greeting. This line here, this is sort of your entry point into the Akka world. The actor system, you can think of it as kind of your container for all your actors. That's the top level that everything else happens inside of Akka. You can have multiple actor systems. You generally won't. It's a pretty basic thing, but you create one and then everything else goes under that. So this piece, there's a little bit of extra stuff in here that seems like conceptual overhead, and it kind of is, but it's important to understand it. This is actually how you create an actor within Akka. This actor of on system, you're saying basically create an instance of this greeting actor. So that's going to create one of these, load it up into the system, and it'll immediately start running. There's this props object, which I'm not going to dwell on, but essentially that causes a lot of people confusion. It's basically a way of defining how to create instances of your actors in an immutable, serializable way. So that's essentially wrapping it up with something that it can pass across the network, because as I said before, Akka is distributed by default, and that's a little hook they use to get around some limitations of the JVM. Sorry. The last thing is just sending a message. This is This is the thing that you'll encounter the most when you look at Akka code or when you're talking about Akka is, this little bang symbol here. So that's also sometimes called tell. It's basically just sending a message. And this is actually borrowing syntax from Erlang. If you ever look at Erlang, you'll see the same notation used. But it's just saying, all right, send this message greeting with the parameter Thomas to the greeter actor. So everybody got that? Seemed pretty straightforward, hopefully? Okay. A couple additional things now that we've kind of got the basic things that Akka gives you is this idea of the actor hierarchy. So as I showed on the last slide, everything starts from the actor system. Once you have the actor system, you start creating actors within the actor system. Those all form a hierarchy, which I'll be talking about here in a second. And there's this supervisor model that goes along with that. And the supervisor model is essentially your basic fault tolerance mechanism within Akka. It also provides flexible message routing. This is something I'm not going to dwell or dig into really, but it's important to know that it's out there. So there's a lot of capabilities within the system for just defining things like fan out message sending. So rather than using that, well, you'd still use the tell or the bang operator that I showed in the last slide, but saying, all right, well, when I send this message, I actually want it to go to these 15 other actors or this undefined set of actors that are over here that I don't want to have to know who it's going to. And then there's this idea of dispatchers. A dispatcher within Akka is a way of defining the scheduling mechanism. So each actor within Akka, it's not a thread. Don't think of an actor as a thread. A lot of people encounter that idea and they get locked onto that. There's some older, early implementations of actors in some other languages, and I think even in Scala where they were implemented on top of threads, directly on top of threads. So when you create a new actor, a new thread was created, and it stayed on that thread, and when that thread went away, the actor went away. Dispatchers are the abstraction that Akka gives you to decouple that. So dispatchers are a way of saying, all right, well, for this set of actors, I want to have a bounded thread pool that maybe starts with 4 threads and can grow to 16, for instance. And it's a way to put that within its own little definition, but detach that from the actual implementation of your actors themselves. Talking a little bit more about the hierarchy, because it's an important idea to get, and it's something that more of the talk will be building on top of later. This is just a very simple way of viewing it. It starts at the top level, the Guardian. The Guardian is internal to Akka. It's something that the actor system starts up when it starts. And it's essentially responsible for making sure that the world is in existence essentially and handling kind of just the top level duties of the system. There's a couple other internal actors here that I'm showing. There's the user actor, which is the top level of the user hierarchy, and it's everything that you create yourself will be under that user actor. And then, this is just showing that. There's also the system actor there. There's a lot of internal actors within Akka that you'll interact with. There's a scheduler, there's a logging handler, so there's an internal logging mechanism within Akka that you can build on that can be fully distributed and everything. It's actually really awesome. And that's all lives under the system actor. Part of the reason I want to talk about the hierarchy is because the supervision model within Akka actually builds directly on top of that. So this is just a very simple system. I mean, it's a little overly simplistic in a way, but just to give you a little example, let's say you have this hierarchy of actors. These are your actors you've created. Don't worry about what they're doing, but you want to deal with the fact that any of these could fail. So they could throw an exception because they're talking to an external system. Maybe the database gives back a connection exception, whatever it is. When that fails, you want that to be decoupled from the rest of the system. You want that failure to be handled in a straightforward way. And Akka does that using this supervision hierarchy so that when that actor fails, it's actually the parent actor that's responsible for deciding what to do with that. So it's making the essentially exception handling, fault handling, orthogonal to the actual business logic and the message handling within the actors themselves. So the supervisor, in this, which is always the parent of the current actor, gets to decide what to do when that failure happens. So it will actually say, all right, well, you had a database connection error. So, all right, that's something that I expect to happen in some cases, and in this case, it's not that big of a deal. So I'm just going to restart that actor, and that's fine. There's actually a number of different choices.
What things happen such that those die?
I'm sorry?
What things happen such that those die, such as exceptions?
Yeah, if you throw an exception with an actor, it causes the actor to, it triggers the supervision process. So just to give you a quick little example, this is just kind of setting the stage for it. So this is a very basic actor that I created just to cause exceptions, basically. So it's actually using one of those internal system actors, the scheduler here, and saying, all right, well, sometime in the next 5 seconds, just die, throw an exception. So this is forcing the issue. Here's the exception hierarchy, the supervision hierarchy. In this case, that exception that's being thrown is one that I've defined. It's this domain exception here. And I'm just saying, all right, well, if that exception happens within a space of 10 seconds and it's only happened at most twice, just go ahead and restart the actor because that's safe. Because I can say, all right, well, I know what the failure context is or what the fault context is for this scenario. These are safe parameters for restarting that. The other thing to notice here is there's this one-for-one strategy. So going back to this hierarchy idea, you have the choice of saying, all right, well, if one of these two actors dies, D or E, and B gets that exception, it can say, hey, restart all the children. So the other alternative to one-for-one strategy is all-for-one. Generally, one-for-one is what you'll use by default unless you have a really good reason to just say, all right, all of you just go away and do something else. The other cases that you can define instead of restart, you can also say resume. The key difference there between restart and restart will actually create a new instance of that actor. And any state that's internal to that actor will be reset basically to the beginning. Resume says, all right, I know that exception may happen. It's fine. That's not going to change the state of the world for that actor's current needs. So just keep running. I don't care. It's no big deal. You can also say stop, which has obvious implications, hopefully, and then escalate, which is saying, all right, I don't know what to do here. Let's punt this up to the next level. And if you do escalate and the escalation goes all the way up the chain, then the whole system stops. So this is building on an idea that's kind of core to the Akka philosophy, which is to fail fast. And if faults happen, it's usually better to say, all right, we'll stop doing anything until we figure out what to do with that. And that's largely about sort of isolating things, and I'll talk more about that in a little bit. So hopefully now I've kind of set the stage and given you enough background with what Akka is, what actors are, that we can kind of build on that and talk a little bit about how you actually build systems with this. And given the time limitations, I could probably do a week-long tutorial on this. Maybe next year I will do that. I just want to show a couple of common design patterns, I guess, for lack of a better term, that you'll encounter, and talk a little bit about why you would use them, and hopefully give you some context so that if you see these problems out there, you know that, hey, I can do it that way, and that's something that's a reasonable way to approach things. There's a few different things that I'm going to talk about real quick. One is about protocols. I mentioned those earlier. I'm not going to say a lot about them, but it's important to understand why they're important. A little bit about workflows. It's commonly what you're doing with actors is modeling workflows. So workflow for your data or workflow for processing the actions that are coming in from, say, user interaction of some sort. And then failure handling, because obviously, as I've hopefully emphasized by now, Akka builds in some key ideas and some key mechanisms for dealing with failure handling at the base level. So when I talk about protocols, sometimes I've had a few people get a little confused about what I meant by that. And I really do like to go back to sort of the fundamental idea of what a protocol is. It's really a way of describing how you're going to interact in a formal way. So you may encounter this idea of protocols in terms of politics and interactions between different parties, different situations. That's kind of what you're doing when you're defining actors, and it's even more important because these are computers. You have a limited number of things that you can define, and you have to understand what those interactions are. So just some key ideas that I want to get across in terms of defining protocols. I've already said this, so this is kind of redundant, but it really is about defining what the interactions are between your actors. A lot of people, when they talk about designing with Akka and actors, focus on defining the behaviors within those actors. The behaviors are fine. You have to define that, but they forget to talk about how you're actually defining the interactions between those actors. So what's actually triggering that behavior? If you haven't thought through all the different scenarios of what could trigger that behavior, all the different responses, then you haven't really thought through the problem yet. So protocols are fundamental. They're also about specifying clear boundaries. So one thing that I commonly see when I'm working with junior engineers or people who haven't worked with Akka or actor-based systems before is that they'll build these gigantic actors that just do everything. There's a lot of reasons that that's wrong and not a good idea. But one of the things that I try to drive home with them as a way to think about it, to sort of get them focused on that, is to say, think about where your boundaries are and define that in your protocol. Define what the actual interaction should be. What are the messages that are going on? Even if you have this big block of code in your actor, like what are the different communications that are going on within that actor itself? I mean, that's basically what your business logic comes down to at some point. And then the other key thing is to understand that your protocol is how you represent state to the outside world, whether that's another actor or an external system. So as I said earlier, actors encapsulate mutable state. They protect the mutable state inside of themselves. So there's no way to go get the immediate value from an actor and look up that memory location inside an actor. I mean, you can sort of hack around that and find ways to subvert the system, but the idea is that you shouldn't do that because that's unsafe. That thing may change in the middle of your trying to read it. With actors, your goal is to instead say, all right, well, I'm not going to let you access my state. I'm going to tell you what my state is. So it's a way of giving the actor the control to say, all right, well, here's the representation of state at the point that you asked me for it. Excuse me. And then another important kind of best practice or guideline that I try to drive home with people is that it's really important to demarcate success and failure clearly. So if your protocol doesn't define success states and failure states, you're not doing it right. I think a good example to look at is just going and looking at things like network protocols. Look at TCP and how it handles these things, and you can see that it's clearly defined in the messages what the success and failure states are. I mean, that's what TCP is all about to a large degree. And I meant to actually find a better example. I apologize that this one is so simplistic, but I just wanted to give some context and show what I mean when I'm talking about a protocol. And this is a very basic one. I mean, it's almost basic enough that it's not all that useful, but this is actually one that I've used in my own code a few times. It's just a way of saying, all right, well, I'm asking for something and I'm going to get a response, and that response is either going to be one of two different things. It's going to be a success or a failure. A trait, for those who don't know it, this is basically an interface within Scala. It's an interface that can have behavior attached to it too, but in this case, I'm just using it as a marker. All right. Oh, I forgot to delete that slide because I didn't find my other example, so ignore that one, you didn't see it. So let's talk a little bit about workflow, because this is where really the meat of defining or designing systems with Akka comes into play. A couple examples that I'm going to talk about, two of the key ones that I think really I essentially end up building in every single system I build with Akka. These are the key things that you see over and over, and yet they're not really talked about in any of the docs. You can find a few blog posts, but the blog posts tend to overcomplicate things or oversimplify things, so there's not a lot of good middle ground. Hopefully one of us will fix that soon. The first workflow pattern or design that you'll see is something I call work pulling. And we'll get into that in a second. And then pipelines are the other key thing. So we'll talk more about these and dig in a little bit on them. Work pulling, it's a really simple idea. So you have two actors. One actor maybe is taking messages in from a queue, like if any of you have worked with JMS or SQS on Amazon or something similar, you may have an actor that's a poller and it's just repeatedly going out and saying, hey, is there any more messages that I need to process? But then you don't necessarily want that same entity to actually handle the processing of that, because you've got different failure cases that may happen. So the thing that's talking to the queue should probably handle those failures and not worry about actually also handling all the business logic failures that can happen too, because those are kind of conflated issues. So if you separate things out, that's great, but then you want to make sure, all right, well, how do you actually make sure that you're not overflowing any one actor in the system? So the pattern that's generally used is this work pulling. So A may be your poller that's going out and checking the queue to see if there's anything more to do. And then B is the worker that's actually doing the processing. This is super simple. There's not much to it. Just get that sort of baked in, because everything else kind of builds on top of this. The key thing about this is that it gives you a very simple form of back pressure. If you're not familiar with the idea of back pressure, this concept comes from fluid mechanics, basically. If any of you have ever had a toilet overflow, that's back pressure. Well, that's one really awful form of back pressure, but the idea is that you want the downstream systems to not get pummeled because your upstream systems are trying to push too much to them. So back pressure is a way of saying, all right, well, don't give me anything until I'm ready for it. And that's all this really is encapsulating. And then, as I alluded to a minute ago, or I guess I didn't allude to it, I actually directly called this out, but this also gives you a way of really decoupling the failure handling. So the thing that's actually queuing up the work handles the failures that are involved in trying to go get that work or receive that work. And the thing that's actually doing the processing of the work can handle the failures that are involved in processing it. So it gives you a way to pull those things apart. It's just a little bit of an elaboration on that same diagram. Yeah, I already pretty much said everything that's on there. So let's look at a real quick example of this. Again, it's just a really simple form of it. So here's my worker. Well, actually first, here's my protocol that I've defined. There's going to be a request for work, and then there's this work object, and work just has an ID and some kind of data attached to it. The worker, in this case, it's doing some really hard work. It's actually going to turn that string that's on there into an uppercase string and log it out. And when it starts up, it immediately goes and asks for some work. And then after it's done processing, it asks for more work. Very simple pattern, nothing to it really. Here's the actual A in the earlier diagram. This is the queuer. This is the thing that may be going out and talking to SQS, or it may actually be getting stuff pushed to it. So sometimes you have chains of these, which kind of dropping a hint about something that's coming up. And there's a few different cases that you want to handle here. So if a worker comes in and requests work, but there's no work to be had, all right, well, and there's work ready, then go ahead and send them the next bit of work that's ready. If a request for work comes in and there's no work available, queue that thing up. Say, all right, well, that worker is waiting for something, so I need to wait until I have something to give them. If work comes in and there's requesters waiting, well, the obvious thing to do is go give some work to them. There's no need to queue it up because that would just defeat the purpose. But if there's no workers waiting, then go ahead and in-queue it for later. And Now, there's some obvious problems with this very simplified example. It's got these unbounded queues in here. So, I mean, this is overly simplified. There's ways of dealing with that. Generally, you use bounded queues and you push back pressure farther and farther up the chain. So this may actually be expressing back pressure to the previous step. It may, if it's actually responsible for going out and talking to SQS or JMS or whatever, it may slow down and throttle the rate that it's talking to that external system because it says, all right, well, my internal queue is already, at whatever arbitrary limit I want to put on that. So that kind of leads into the next pattern that I want to dig into a little bit here. Pipelines are sort of the most typical thing that I find myself building with Akka. Really, just about every system that I've built can be modeled as a pipeline. So it's a very that statement in some sense has no content from my perspective, but I think it's good to recognize that even a basic web service can be thought of as a data pipeline. The pipe is a request comes in, do some processing, response goes out. That's a pipeline. It doesn't have to be complex. But typically there's a lot more involved, and you have more stages to that. So, excuse me. These are commonly found in data processing applications. There's usually distinct phases of responsibility within the system, and then it's not uncommon for these to actually span across multiple systems. So this gets into the distributed part of this. And then often you'll have different pieces of your pipeline actually have very different scaling concerns. So the piece that's actually talking to your database may have to scale one way, but the piece that's actually doing the image processing may scale in an entirely different way. So understanding how these pipelines are put together is helpful here. This is a very simple view, a common way of looking at it. Each phase within here can have its own failure domain. So ingest will have one set of failures that needs to handle. Digest, where you're actually doing the processing, may have another set of failures that it has to handle. And then that should say egest, but a whole other set of failure cases. And then again, you have back pressure within this pipeline. This is still actually simplified from a lot of the systems that I've worked on in the past, but this gives you a little bit more context of kind of what these systems start to look like pretty quickly. You have different stages and phases of processing along the system. And then again, just to re-emphasize this, each of these phases, what happened there? Has its own failure domain. You've still got back pressure through the whole system. Man, it's the problem with using a new clicker that I haven't used before. The model still applies. This is really, though, just an extension of that same pattern, the work pulling pattern that I showed before. So there's not really anything more to get here other than that you're essentially breaking it out into more discrete pieces. It's pretty much always, or should always be modeled with work pulling, so you want to understand how that works. And then the other thing that I'm going to say here is that building those systems can get really complex, and there's a lot of details that you need to keep track of, but there's a project that's just now coming out called Akka Streams. It's been in development for a long time, but it actually simplifies a whole lot of that. So if you really want to dive into a much nicer, simpler way to do that, keep an eye on that. I think I'm actually out of time here, but is anybody keeping an eye on the time? I'm not really sure. What's that? Oh, okay. What time is this supposed to be over? I can't remember. Okay, good. I've got 5 minutes. Plenty of time. So the last thing to get is fault tolerance. And this really is built into the core, but there's a few things that you should think about when you're designing these systems. The first one is circuit breakers. A lot of people first kind of got exposed to this. I said I wasn't going to mention Netflix, but I am going to mention it. A lot of people really got exposed to this when Netflix released their Hystrix project, which was one of the first sort of high-profile implementations of circuit breakers on the JVM. Akka actually has an implementation internally. It's actually really simple and very straightforward to use, so I'm a big fan of it. The key idea with circuit breakers is that they help you isolate key components of your system, or isolate from external components of the system more commonly. And then the other key thing to understand is fault isolation and failure domains, which are really about restricting the size or the scope of impact when failures happen. So here's a basic diagram of how circuit breakers work. I'm not going to go into this because I could probably spend the next 4 minutes and however many seconds just going through all the different. This is just a basic state model showing how circuit breakers work. So the idea is that you're typically in the closed state. That's your good state that you want to be in, where the circuit's closed and you can actually talk to whatever you're trying to communicate with. Then you have this open state where a failure's happened and things are going wrong, and you don't want to blow up because you're trying to send stuff that won't go through. And then there's this half-open state that you get into when you feel like it might be safe to start talking to this external system or this external component again, but you want to keep some tight control on that. So again, some of the key ideas here, it's about isolating important components or isolating yourself from other components of the system. And then you really should think in terms of avoiding cascading failures. So you don't want one system to go down and then it cause every other part of your system to also fail. Your system may still be able to function even if that one system is down. Just to give you a little bit of understanding of how simple these are to use in Akka, this is again just sort of setting up sort of a dummy for showing the example. It's just an actor that occasionally when it receives, or after some random interval, will just cause an exception. Very simple, but the default case, it will actually send this or reply to this message with an uppercase version of the string that it received. And then here's an actual usage of that. Basically, the bigger context here is this is an actor that's just sending itself a tick message periodically, so it keeps trying to send things to this other actor. And it's just going to send some random string to it. And typically, it's going to send that, then it's going to get that back, this decoupling with the pipe 2. We don't need to dwell on that. If anybody has questions about that, I'll explain it later. It's just a way to keep things responsive with an Akka. But typically, it's going to send this message, it's going to get the response back, and it's just going to print it out to the log. That's fine. But occasionally, that other actor is going to fail, and that's fine too, because I've wrapped it with a circuit breaker. That circuit breaker, again, similar to the supervision strategies that I showed earlier, has some context that you can put around it, so you can define, all right, well, allow a maximum number of failures before you go, into the fully closed state, and then set a timeout so that at some point it will actually trip and reset, so it will actually try to start sending things again. Because once you're in that closed state, you don't want to stay in the closed state if some things become healthy again. You want to eventually try it again. So that's about as simple as it gets. And then the other thing, just real quick, I'm going to speed through this, just because I've got like 2 minutes, like 30 seconds left. It's failure domains and fault isolation. This is really something that's kind of been implicit through all of this, and it's implicit in the way that the hierarchy and the supervision strategies work within Akka. And the idea is that you're really trying to break your system up into these isolated components that each have their own failure domains. The reason you want to do this is because each of those have different concerns. Each of those has different scenarios that they need to be able to deal with in terms of what may fail. So if your ingest system is pulling from a message queue, that message queue, I think I've said this like probably a dozen times already in this talk, is going to have one mode of failures that you need to handle. But the rest of your system shouldn't care about those failure modes. It shouldn't have to worry about that because that's not its concern. So basically this hierarchy, this is really just re-showing what I showed earlier, as I was saying. It allows you to have these failures. So if your ingest system is trying to maybe push these things to some kind of storage system, and a failure happens, you don't want your ingest and digest components to have to care about that. I mean, yeah, you may have back pressure so they don't keep trying to process messages when the rest of it can't process, but there's no reason that they should just go away and die unless that's what makes sense to do. Thought there was another slide there, but that's pretty much it. And we are out of time, but I can take a couple quick questions if anybody wants. Sure.
So you mentioned mutable state several times. My understanding was that you're supposed to prefer immutable state.
You prefer immutable state, but computers have mutable state. You can't avoid it. There's going to be cases. There are ways within Akka to make mutable state a lot easier to deal with, and even model what at least seems like mutable state as an immutable thing that just changes over time. And I could do a whole nother talk on that, but mutable state is something that you will encounter sometimes, and it will be hard to get away from. Sometimes you just want to accept that you have to deal with mutable state for efficiency reasons. So if you're dealing with a system that has to be really fast, sometimes allowing mutable references can save you a little bit of overhead. So this gives you a way to deal with it without having to necessarily say, all right, well, everything's mutable and now anything goes. So you can isolate it when you need to. So anything else? Dave? Good question. There's not really a good collection right now of patterns within Akka. It's something that's been bothering me for a while. There's a little bit in the Akka docs, and then there's a whole bunch of blog posts out there which are varying qualities. I actually bought a domain about a year ago, meaning to set something up and start putting some of those. I actually have an outline that I started putting together with a bunch. So I'm hoping to get that out there soon. If you're interested in that, hopefully I can finally find some time to do it after this. Just if you didn't see it, the first slide had my Twitter link on there. I will be posting it on there once I finally get it out there. So, but there hopefully will be something soon.
So does Akka do any sort of bounded queuing between actors for you? Or
Yes.
Do that yourself inside?
It's totally configurable. So that's something that you can do entirely within the configuration. You can build your entire system, write all the code, and then later on define what those bounded queues look like, and define whether they are bounded or not, actually. So that's really easy to do. Anything else? All right. Thank you, everyone.